Okay, well, let's get started. There's not many people here, but I'm sure a couple more people will roll in. Yeah, so we've kind of run off the end of the official course notes. So I'm just going to fill this lecture, or hopefully fill it, or maybe partly fill it, with some demos, like kind of maybe which will help you with the last project. And I'd also just like to say a little bit as well later on about how to make your Julia code fast. And if we've got time, I might throw in some bonus metaprogramming stuff just for kicks. So like we might show how to implement the @_ macro that we were using the other day, just a little kind of toy version of it. So yeah, that could be a fun little bonus thing, hopefully fun. But yes, that's what we're going to do today. So I really don't know how long that's all going to take. So I'm just, yeah, we'll see how we go. Okay, so the last task, who's had a look at the last project? Has anybody read through it? Kind of. Nobody's read through it, really? Okay, that's fine. Yeah, no worries. Yeah, okay. So people haven't really read through it. That's not a problem. So I was just wondering, because like so the context of this first part, I guess, is we're going to do a bit of interactive plotting of data. And in the very last question of the project 3, there's a comment there that you should maybe use Makie.jl to make an animation of how like I think it's the locations of houses. Like we can actually go and look at it. Let's have a look at that. We can easily do this. So yeah, so task 5 in the assignment is to plot the location data over time. So of the Melbourne housing data. So you might want to have a map of Melbourne in the background and then show how like where houses are being sold and the prices of them maybe in some graphical kind of way. So yeah, it's recommended in the project to use Makie.jl for that. So I'm just going to give you a demo of how to use Makie for some stuff. So we're going to go and use our previous data set that we had from Unit 8. So the one with the athletes. It's probably not quite as, actually, maybe not quite as exciting as the spatial data in the Melbourne housing data set, but that's okay. Yeah, and I'll show you how to make a little interactive widget that you can play with the data, because sometimes it's all well and good to kind of make one single plot of like say 1 year worth of this Olympic data set, but you might want to know how it changes per year and like fiddle around with that interactively. So that's what we're going to do. Okay, so let's get started by, yeah, so just loading some packages. So we're going to be using data frames and CSV. Whoops, I got that in there twice. And underscores, which are those packages that we were using for data analysis last time. And also statistics. And we're also going to use GL Makie. So yeah, Makie is a bit like, I mean, it's pretty much like has similar functionality to plots.jl. So you've been using plots this whole time. But Makie is written in pure Julia, and it's sort of a bit of a different focus. It's like kind of really focused around interactive data analysis. So being able to plot large amounts of data fast. So it has hardware acceleration in the OpenGL backend. That's what GL here is in GL Makie. It uses your graphics card to make the plotting fast, and also make it pretty. So that's nice. Yeah, and it's also designed around interactivity as well. So we'll see how this kind of, we'll have a little quick look at how reactive programming works in GL Makie. Okay, so let's load the data. It's the same as last time. So that's just the raw data that we've got there. And what I thought I would do was, so one thing that occurred to me when we were looking at the data last time was that if I just go back to the Unit 8 notes, there was this, whoops, let's go to the bottom. So there was this graph, this histogram here. And that's like for 2016. And I thought it would be interesting. Like my curiosity was just triggered by looking at that and going, well, what does that look like in other years? And of course you could just go and like put some other numbers in by hand here and just make this plot again and again. But what would be even nicer would be if you had a slider somewhere, which you just grab and slide backwards and forwards and see how does this histogram change depending on the year. So that's what we're going to do. Okay, so, and we're just going to restrict it to the summer data, the Summer Olympics data, just to avoid any issues with, it just makes the code simpler. So we're going to filter this. So from last time, you remember that this says that the season column is going to be used to, and we're going to compare that to summer with the equals operator. And we're putting this data through this pipeline. So that's the data going into that argument there, that placeholder. And we're calling the filter function on it. So yeah, and also I'm going to use pipelines through this whole thing because I like pipelines. Okay. Right. So we're also going to need the years that occur in the data. So we can easily get that by just uniquifying all the years and then sorting them. We want them in order. So there's the years. There's not actually that many. I guess given it only occurs every 4 years, then yeah, kind of makes sense. Although in these early years, it's occurring every 2 years. Okay, so and in order to look at this data or create like a version of this per year, what we want to do is group by both the sex and also by the year. So that's what we do here. So we've got the summer data, and I'm not going to uniquify this. I've commented this out. I'm not, like previously we'd unified it by the athlete's ID, but the athlete can compete in multiple years. So I think it makes sense to let the athlete occur multiple times in this data set. We're going to let them happen. We're going to let the athlete be in each year. Well, I guess for height, they're probably not going to change height, but if you're looking at participation or something like that, how many people are in different sports and stuff, then that would be a good idea. You should leave them in and let them appear in multiple years data. So we're not going to unify by the ID. We're just going to group by the year and the sex. Okay, so we've got our grouped data frame. We have 57 groups with those two keys. Okay, so here's where the plotting comes in. So GL Makie is the package you want to use if you're doing interactive plotting. So that's sort of stuff that's going to happen on your own computer and you're just interactively playing with it. And if provided you have a graphics card, which nearly every machine does these days, have an embedded graphics card, then you should use this one. There are other backends. So if you want to make some publication quality plots, or you've got something you want to put it in a PDF for your for making a report or something, then you can use Makie, which that just uses a different way of like generating the plot data. So rather than using the graphics card, it will use some CPU code, and that can be good for like making really high quality plots, but not so much good for doing interactive stuff and for doing 3-dimensional data and those kinds of things. So yeah, this one's the one you want if you want to do sort of very interactive application. And all of these, by the way, have the exact same API. Like the functions you call and use are the same. It's just in the background, it's using a different engine to make the pictures. Okay, so we'll use that. So yeah, we'll also see layouts here. Oops. So if you want to place multiple plots in different, or multiple plots into the same kind of window. Okay, so here we have an empty figure. It's very boring. It's white. And maybe I'll just skip over this bit to start with, and we might just plot one single year. So let's go with a histogram. So what I'm going to do is I'm going to slightly modify this stuff here. In fact, let's do this. So we're just going to start with the simple version. So we've got some heights here. So this is similar. Oh, we've got to get rid of that dollars there. Okay, so we need to choose a year. So let's just choose 2016 or something. So here's the simple version. Okay, so we've got some heights from that year, 7,000 participants who were male. And let's plot that into, oops, that's not good. This is going to complain now. I got to start again. Okay. Yeah, so let's plot that. Okay, so we've got a histogram. That is just similar to the plots histogram. There's nothing too exciting going on here. It does have different options, like the names of options are different, which is slightly irritating if you use those packages. So if you want to like do sort of an outline for those bars on the histogram, then you need like I think it's this in like graphics jargon, the stroke of a shape is like the outline. So that's why we're using stroke color as black or something. And so I think this could work. We also, the other thing you might notice here is we've got this figure. I'm just going to delete that. It will then start again. Just so like these commands, for instance, hist for histograms, if you don't specify which figure you're plotting into, then it will just make a new figure. So that's what we've got here. So you can see that we've got these outlined. I think for the later example, we'll just keep them not outlined. But yeah, there's all the options to do the same kind of things that you would do in plots. Okay, so yeah, so that's one single histogram. So, but what we want to do is make this interactive. So what we need to do is like create a slider, which we can slide around. So let's do that. And not only do we need the slider, but we need some way of connecting up the value of the slider to the current data, which is in the histogram. So that's the tricky part. So let's do that. Okay. So here's our slider down the bottom. It's not very interesting yet, but we can slide it, and it has the gear printed out. It's actually hard to see, sorry. I'm not sure how to make that bigger. I wonder if there's a way of doing that. I don't know how to do that. So yeah, if you can't read it, then sorry. Yeah, I won't mess around trying to figure out how to do that right now. But yeah, so the year is printed in the bottom right, and we've got the year label, and you can actually make multiple sliders. So if you have several different properties that you would like to change, then you could do that. In fact, maybe we could do that in a minute. We could just have a single histogram with like the guys or the girls, and have a slider for just toggling between those as well. Slider's probably not the right thing for that, but we could do it. Like you might want a button or like a box or something, and those I think those components exist as well. But yeah, okay. Okay, so here's where the interactivity thing comes in. So this line here is getting out the value of So this is a grid of sliders, as I was saying. You can have several sliders, but in this case, we're only using one. And the reason I'm using slider grid rather than a single slider, which you can also do here, is that it gives you the ability to label it really easily. So that's convenient. Okay, so this bit here is getting out the value of the first slider. So let's have a look at what that is. Oops, I've done something funny. Okay, so this is where it gets interesting. So the value of this slider is currently 2000, but if we were to move, maybe I'll just make this do that so we can see both at once. So if I was to move this around, then the year is now 1956. So you can see that somehow, magically, maybe, this year value has been updated by this graphical user interface component. And so what we actually want to do is also make the histogram itself be updated, or the heights that we've selected be updated based on the year. So this is how we do that. I might show you the uglier version first, just because it's a bit more explicit, and then we'll show the really neat version. So let's look at the male heights. It's this little bit of code here. So what's going on here? Well, we're using this function called lift, which, so you can see that year here isn't, its type is observable. So what an observable is it's a reactive software component. So it's something that will push any changes to itself. So we could actually set the year as well. So we can set the year to like, let's say 1996. And now we can see it's also correctly set there, I think. Let's do that again. Oh, okay, so that's interesting. Something has gone a little off there because this should update. So I'm not sure if that's the correct way to update the graphical interface. There might be something else we also have to do there. But what I wanted to show is that you can make things which depend on year. So we'll do that with this one here, this piece of code. So male heights for that year are going to be, you take the current value of this observable. So this observable wraps a value. It's not the value itself, but it's a wrapped version of that value. And it also knows about anything that might depend on it. So that if it changes, it can call some functions to make things which depend on it update. So that means that everything downstream of year, like things which are computed from it, like these heights, will automatically be updated when the year updates. Okay, so let's actually run this piece of code. So what's going on here is that lift is a function which it takes this function here. Remember, the do syntax creates a function. So y is the value of the year. This is the observable year. This is the value of that observable at some update. So what we're going to do is use the value to do this collect thing that we did before, right? So yeah, that's just like this line here, except that we're like giving it this function. It can compute later on if the year updates. So yeah, that's what lift is all about. It's a bit of a confusing thing, maybe. Does that make sense to people? I'm over-explaining, under-explaining. Yeah, would it be like a while loop where you just sleep and then like for 1 second and then check whether it's updated? It would be kind of like that, except it's more efficient because you don't need to poll it. You don't need to check it's updated. You don't need to recompute anything. So it's just automatically updated whenever the year updates. But yeah, it's a little bit like having a loop running behind the scenes, which checks this variable all the time and then continually recomputes whatever it is. Or maybe it checks whether the variable's changed and then it recomputes if it has or something like that. So it's a little bit like that, but way more efficient and convenient. Okay. But yeah, the syntax is a bit strange to use it. You have to keep using this lift function all over the place. So there is a way of I guess one thing in Julia though is when you have syntax which is displeasing like this, you can always write a macro to rearrange the syntax so that it's nicer. So that's what we get with the @lift macro. So if you have a look at this line here, you can see that it's just it's different syntax for the same thing. So what we're saying is that we're going to use this variable year. So the dollars in front of it means that that's coming from outside the context of this expression. So it's this like this global variable year from over here. And that is the thing which needs to be lifted. So what this macro @lift does is it takes this expression and then generates an expression that looks like that. So yeah, one of the issues you do have with using lift is that you really would like to do this kind of thing. Like then you have two different years though, like two different variables here. There's one inside the function, these ones, this bit, and there's one outside the function, this bit here. And they're different things. One of them is a value and one of them is an observable. So like I always find that displeasing. So it's nice to use the @lift macro where you don't need to invent this extra dummy variable. Okay. So that's what that's about. So we can make two new observables, male heights and female heights. I'll just copy those over. Okay, so let's have a look at those as well. So currently this has this inside of it, right? But what if I was to change the year? So I'm going to put it over here. Has this actually changed? I hope it has. Yeah, look, it's changed. So I'm sliding the slider around. And as I do that, this observable here is sort of magically changing. It's not that magic, really. I mean, this slider is just triggering an update on the observable year, and then that year as observable is triggering this function, this piece of code here to run, and then it's updating the value in the male heights observable. So this, and note that this is an observable. This is not just an array. It's an array wrapped in this observable data structure. And if you want to get the values out, you can just do this. So this is the actual value that's inside of it right at the moment. But if you just have that, it's the wrapped thing. Okay. So all of Makie is kind of built around this as the kind of core like way that it does interactivity. You make these observables and then you make things, other observables that depend on them. And those things can be connected up to the user interface components. Yeah, so then everything can be nice and interactive. So let's create the actual histograms having made all of that explanation. Okay, so now I have this situation. We've got our nice little slider down here, and hopefully, oh, okay, so I wonder what's gone wrong. We might have to figure out what's gone wrong there. I might just rerun all this code, and it might just be that I've been explaining a lot and have run things in the wrong order. So let's just check whether that's what's going on. So we'll recreate it all. It's also possible something else has broken. This was working earlier though, so okay, no, it's something to do with me running things in a funny order, I think. Okay, so now we can actually drag these around and see, oh, there's see how things have changed. And in fact, I've also got these in different positions in the figure. So I don't know if you've played around with how plots does that, layouts and stuff, where you have like one plot over here, one over here. But if you have, then it's similar kind of thing. So the figure itself can be indexed, and these indices are just like matrix indices in terms of like where on the figure they end up. So yeah, that's how you do layouting, really simple layouting in Makie, but you can do other more complicated things. So what we'd actually like to do in this case is overlay these histograms. It's nicer to see it that way. So I'm going to use the exclamation mark here to plot on top of this figure 1.1. So we're going to have both of those in there. And yeah, we've put the slider in figure 2.1. So that's why it's down the bottom here. Okay, so we do need to run we do need to run this again. Makie will get upset if you mutate. Yeah, if you kind of like put something in a figure and then try and call hist again on the 1 slot of the figure without the exclamation mark. So we just need to recreate the figure from scratch. Okay, so yeah, this is the final little demo, the final little example, I guess, of this. And we can see that we can sort of also the normalization doesn't change. So we could fix that if we could bothered, but you can see that the participation has gone up, obviously. And that's another interesting thing that you'll just see in this data now, really obviously as well, is the like ratio of men and women participating has obviously changed a lot over the years. And this is the height histogram as well. So another thing that you also can see in this data is the fact that the mean of these is going up a bit over time. So this is a little jerky, I'm afraid. Let's make it a bit smaller. Not sure why that is. But yeah, so if I just slide these around, you can see these histograms sort of shifting. Oh, and I am avoiding the very left-hand side because there's no data for females in some of those years, and it's broken something, and I don't want to make the thing crash. So that's why I'm avoiding that side. Okay, yeah, a little bit dissatisfying, but I didn't figure out how to fix it in time. Okay. I think I've kind of done this as part of the other demo, just showing you how observables work. Okay, so that's the sort of interactive Makie demo bit that I thought of giving you. So any questions? Yes.
Question, but it'd be really nice if you could like made it at the normal curve and then animate it like smoothly over time.
Right. Yeah, we could fit these histograms with some kind of distribution. What's the best way to do that? I think it would take me a little while to do that. We can do that if we have spare time. Maybe we should try and do that actually. Yeah, like we could fit each of these histograms, or we could fit the normal distribution to the data. Actually, you don't do the histogram and then fit the distribution. You just fit the distribution directly to the data points. That's because remember, this histogram's already a summary of the data. So we could plot some other kind of plot showing the actual samples. That could actually be interesting. So by the way, here's the Makie home website, docs.makie.org. This is really good. It has a lot of examples for all the sorts of plots and things that you might want to make. So perhaps we could find, I think it's called a violin plot or something. There's plots for plotting. Sorry. Yeah, there you go. There it is. There is one. Okay. I'm not sure if that's the one I want or not, but no, that's not quite what I want. This is for plotting distributions. Yeah, exactly. You can have many together. It's not exactly what I want. I guess if you were going to do this non-interactively, then that might be a nice way to do it, because you could have a sample of different numbers, different years, and then you could have just a sample of, say, 10 different years. I was after I forget the name of it. There's a certain type of scatter plot which is good for plotting distributions, but I've totally forgotten the name of it. I think we might just continue, unless someone can. Yeah, no, yeah. No, it's anyway, yeah. Just gonna continue, I think. Okay, yeah. So we can come back to trying to fit those. I'm just oh, I don't have off the top of my head the exact function I need to call for that. So I would need to go searching for it. Okay, what else have we got here? I don't know if this is worth looking at, but you can ask other questions of this data. You might want to know what the popularity of the sports are. for instance. So this would be a pipeline that does that. So you take the data, you group by the sport, and then you can use combine to compute the number of rows in each of those groups. That's what that's about. And then you can sort by the count, the popularity of it. So we could run that little example. So here's and this is over all the years. So we just combined the years and we've ignored the fact that summer and winter exist. So yeah, I mean, this isn't a very good label. Like athletics, I mean, really, there's a lot of different types of athletics. So like big surprise, it's popular, but there's a lot of subcategories inside of that. Whereas, I mean, that's probably true for all of these top ones, really. Even fencing, like there's several different things. So I don't know. That's surprising. Like fencing, is that popular? Okay, that's cool. Anyway, yeah, so we could find that kind of thing out. Or we could like look at that over time as well. So in that case, we would potentially group by the year and also the sport. And then we could use that data to, it's just the same as before, but with the year in there as well. I mean, then we could use that data to plot a bunch of line plots, say over the years, for how popular the sport is. So anyway, I don't know if we need to run that one. Well, we can run it. It's not that surprising. So yeah, we've got now it's got year and sport there in the oh, and this actually this sorting isn't all that sensible. We probably want to sort by, well, I mean, what are you going to really sort by in this case? We don't really that doesn't really make sense until you kind of group it by sport or something and then sort by the year. Anyway, like maybe you would sort it by year. Anyway, yeah, so we could use that to make a line plot over time, for instance. So if we do that, say we filter by sport, like rowing is a popular sport. Whoa, oops. Okay. I'm doing silly things, apparently. I just want to do this. Okay. Yeah, so if we filtered it by that, and actually we've got that sorted by year, yeah. Okay, and so we could just assign that to something and dot, what is it? Oh, it's surprising. Okay, so then we could just look at the count and the year. So lines from Makie. So that's a line plot of the popularity of rowing over the years of the Olympics. That's not a very interesting plot. But it might be interesting if we were to look at all the different sports and kind of, or maybe the top 20 like popular ones and plot how their popularity changed. We might find that some of them became less popular, for instance. So yeah. Okay. So yeah, anything more people want to know about this sort of data filtering and stuff, or any thoughts which are triggered by that little demo, or we can go on to making Julia code faster, which is something we missed out a little bit on earlier in, I think it was unit 7. Could you make the transition smoother? Well, I mean, the data is inherently discrete because you only get the Olympics every 4 years. So you would have to interpolate something. Oh, that could just be that I'm using Zoom and it might look better on this screen. So, oh yeah, that's true. So if you had a large amount of data, you might need to pre-compute it. I actually feel like there's something with my graphics card being bad because this computer's is pretty old, which might be why when I had it full screen, it looked pretty jerky. More so than anything to do with like the CPU side of this computation. But yeah. A map in the background. Yeah, so right. So in project 3, there's a map that you need to place in the background. So I think there'll be an image. Let's have a look. No, those are the components. Okay, so yeah, in the reference here, there's a bunch of components, which are like the interactive components and stuff. So there's boxes and buttons and all those kinds of things. And then there's the types of plots below. So let's see if we can find image. Yeah, so there's an image function. So yeah, how do we get images into it? Well, we could do these kinds of things. They've got one of the cow here. So if you were to get an image of the Melbourne area, the main thing that you're going to need to be careful of is the coordinate system. So you're going to need to find like one which is in latitude and longitude, for instance. Like that's good enough for Melbourne, I suppose. It might be nicer to use a different map coordinate system, but like that long will probably do for this use case. Yeah, so then you just need to make sure it's scaled correctly. So there's examples here of how to sort of flip them up and down and stuff like that. So that's probably going to be the most irritating thing, is getting the coordinate system right. But as soon as you've done that, then you can just, you can use this image function to plot your little picture. And then on top of that, you can plot your scatter plot or whatever it is of data that you would like to have. So in your data set, presumably there's going to be like a latitude and longitude for every sail or something along those lines. So then you can overlay those on top of your map of Melbourne. Yeah, so I'd probably do it something like that. There are like specific geospatial like libraries and stuff that you could use in Julia. And there's a lot of that kind of thing. But I think for this, like, it's probably easier just to do those little bits and pieces yourself. As long as like you're given the coordinates in a sensible way, like if they've given them in lat long, for instance, already, that's probably good enough and you don't need to transform them. So yeah, it might not be worth delving into one of the geospatial libraries. You could probably just use Makie. But yeah, if you do need to transform latitude and longitude to some other coordinate system, like one of the mapping ones that we actually use in Australia, like Universal Transverse Mercator or one of the other ones like that, then yes, there are libraries to do that stuff. Yeah, so I think, coordinate systems is going to be the big pain. So once you've got that sorted, I think the rest should be easy. Yeah. Okay. Yeah, thanks for the question. Okay, so next little section. Oh, we've actually, used more time than I expected on all that. So I don't think we're going to get to the macro demo. But I'd like to say a little bit about this. So here's just a really bad way of adding some things together. So I've got this function here. In fact, like the fact that it adds things is kind of irrelevant. It's just an example of a function which has a performance problem. Okay, so let's run it. Let's see. So what are we going to do? What we're going to do is, so you can actually see that this just computes the sum of all the things in XS. It happens to. So I'm going to use this package benchmark tools to figure out how fast it is compared to the built-in version of sum. So does anyone see any performance problems with that, by the way? Oh, okay. So we're going to have nums, which is going to be like a random array of 1,000 floating point numbers. So there we go. So that's just our test data that we're going to use. So Benchmark Tools has a tool called btime inside of it. So that will allow you to time things like this. So btime is just a better version of @time. It does like calls the function once to make sure that Julia's just-in-time compiler stuff has been done. And then it will call it a number of times and do some statistical measurements. So it'll also tell you how many allocations, just like @time does. Anyway, so that took 21 microseconds. There's also another one I'd like to show, which is benchmark. So this btime just produces a number, which is actually, I'm confused. Oh no, okay. So yeah, this it just reports this line here and then returns the value from the this function invocation. But @benchmark does a lot more. It can show you the distribution of times. So it shows you that the very fastest that it could do was 22.4 microseconds, and it even shows this little graph of it, like it's a histogram of all the times that were taken. I think this vertical axis is a log scale, so this is highly emphasizing this area here. And it's showing you the median and the mean, and also the longest time that this took was 118 microseconds, which is actually crazy. So there's a huge variation in the amount of time it took to run this little add things function. So yeah, has anybody spotted like the worst thing that's going on here? There's one thing which is really bad. There's some other things which are kind of bad. Sorry. Yeah, but in terms of the code, okay, so the other thing I should do is show you what what the time of sum is. So it's 99 nanoseconds. So basically 100 nanoseconds to sum 1,000 floating point numbers with the built-in version of sum. And this thing, which is achieving actually the same thing, is taking 22 microseconds. So that is 200 times slower. So we're going to use code warn type to. So this is a tool that's built into Julia. And what it does is us type inference what's going on inside this function in terms of all of the variables. So what we're going to do is run that. So unfortunately, what this does is also talk to you in terms of the lowered code, and that's not very easy. It's like a halfway to machine code kind of thing. And so it's like an intermediate representation of the code. So it's a little, well, it's pretty hard to read. But basically what you should be looking for in code warn type is, are there any red things? There is a red thing here. And so this says basically that type inferences said S, this variable S over here is any. It has not figured out what S is. So can you tell me why it can't figure out what S is? So it knows the X's that are coming in. Oh, wait, that's the other thing we should point out. It knows X's is a vector of float 64. So it's very sure that what that is. And it knows that if you, let me see, get filled. Oh yeah, no, that's not that easy to read, but it's detecting that there's float 64s in here. So yeah, no, this is not super easy to understand this lowered code. Anyway, but the point is S is any, and okay, I'll tell you the reason. So the reason is that Z is a global and it's not const. So this could be set to anything. It could be like, we could do this later on. It's a string. So Julia's just like, oh, well, there's a reference here to this global variable Z, right? And that could be any, like it is any, it could be anything. So I think that's one thing, like there's some example code in previous units where there's global variables, they're not declared const, and this makes everything really slow. So if you declare them const on the other hand, I'm just going to do this. Yeah, okay. So I think we have just enough time to kind of finish talking about code warn type. So I'm going to make this new variable Z1 because you cannot create a new const in the same session with the same name as something that's not. So anyway, I've just run that code. So now I've said that Z1 is const. What that tells the compiler is this binding is constant, and it can know that the type of this is always an integer. So type of Z1, that is an int 64. Okay, so now if we b time this new version of, should have called it something else instead of the same thing. But anyway, so if we benchmark, we time that again, now we should see that it's a lot faster. So before it was 20 microseconds, now it's 2 microseconds. So that's pretty typical. So what you'll find is if you have any's in your code, you're losing a factor of 10. It's 10 times slower. So yeah, that is bad. So now if we look, but now it's not so bad. It's still pretty bad compared to the built-in one. But if we look at code warn type now, we've now got some yellow things. So like red things are really bad. Yellow things are just a bit bad. So we'd also like to remove those. So what's going on here is Z1, and let's remove this as well. Like if you can remove your globals, go ahead and do that. So we'll do this now. So I have this version of it where we've just set S to 0. Now, this is going to be the same. There's some yellow things in here. And that means it's not like any, but it's not a fully concrete type. It's one of several in this case because it's a union. So what's happening in this case is that S starts out being an integer. It's 0, not 0.0. So it's an integer. The things inside X's are floats. So in the first iteration, S becomes a float and stays a float for all the rest of the iterations. But Julia can't know when it emits the code because this code inside is going to run for every iteration. So it's including the first iteration, then all the others. Sorry, go on. No, so yeah, a float plus, even if it's, so 1 plus 0.0, always promotes to float. So S becomes a float in the first iteration and remains a float always. So the way to fix this is to use, if you're writing generic code, you would probably use this kind of thing. So you'd ask what the element type of X's is. So that will be a float, or maybe it's integer, depending on what this variable, this thing X's is. And then you'll ask for the 0 identity, the additive identity, which is what the 0 function returns for that type. So if you do that, we end up with this version of it. I mean, if you knew this was floats, of course, you could just do 0.0. That would also be fine, but this is the sort of generic way of writing this code. So now if we ask code warn type about that, we've only got one thing left, which is yellow. Everything else is, and I'm like, now what is that about? Tuple of nothing. Oh, okay, yeah, I know what that's about. Yeah. This is due to the way the iteration protocol works. I'm not sure this is an actual performance problem. That may be. Anyway, so we could probably fix that one as well. So when you do X in X's, that's like invoking the iterate function. But I think what's happened here is that it's turned inlining off to get code warn type to work. So we could possibly, yeah, no, I won't delve into that because we're running out of time. But you can also look at code typed. That will have optimization on. Yeah, so you can actually see in code typed. It's expanded out quite a lot. So what's actually happened here is it's inlined a lot more functions. So in an attempt to make the warn type code a little bit more easy to understand, the inlining is turned off. But once inlining is on, the optimizer is able to do a better job. And you can see that there's actually no unions left in this code. So in that case, code warn type was just a little bit misleading, actually. Anyway, so having done all that, we can now b time this new version of add things. And And now we're down to 1 microsecond. Now, surprisingly, perhaps, that's still 10 times slower than the built-in one. And that's because the built-in one is using SIMD instructions. So like it uses the CPU's internal instructions to add 2 floats or maybe 4 together to double precision floating point numbers, or 4 depending on the width of the SIMD units all at once. So it's just much more efficient. So the thing is though that like someone has optimized the heck out of SUM, is that like summary about that. So yeah. There's a lot more that you can do in this particular case to make it really, really fast. Yes, question. Yeah, you could do it in parallel. It is really easy to do in parallel. So if you had a really large data set, you could definitely like put @threads in front of it or something like that. Yeah, so you could definitely try doing that. The built-in SUM doesn't do things in parallel by default. Yeah, generally speaking, like the built-in functions in Julia, except for a few of them like matrix multiplies or matrix like factorizations and stuff, don't have parallelism built in. And like the real reason is I mean, there's multiple reasons, but one of them is basically it's hard to know that someone's going to pass you a really long thing that you actually want to parallelize things on. I don't know. So and for something like SUM, you might actually be bandwidth like limited anyway in terms of getting like data from your RAM. So there's like multiple reasons why you might not want to parallelize all the things. But yeah, generally speaking, most things aren't parallelized, and you need to like do a little bit of manual effort to parallelize them. Just like a few libraries which is really highly worthwhile, like matrix code, are parallelized by default. Okay, and I guess that's pretty much time to wrap up. What I'm going to do is just give you a little tiny taste of another thing. So there's all these macros here. We didn't get to jet. There's all these macros here which let you inspect the code as it goes through the compiler. So there's this code lowered, that's sort of untyped IR, intermediate representation. There's the one type, there's typed, which we've seen already. So those ones come from the like type inference and the optimizer, the Julia level optimizer. And then there's LLVM, which is kind of almost machine code. Low level virtual machine is what that's about. It's a library that Julia uses to emit machine code. And then there's code native. So if you like to read assembly, then you can look at the assembly in the REPL. So anytime you want to see, oh, is the assembly that's being emitted for this sensible, you could go and look at the assembly code, which is actually being generated. And you can see it like interactively. You can change your function. You can see the new assembly for it. So yeah, if you're doing low-level optimization, that's really useful. But you have to know roughly how to read assembly. And I don't know how to write assembly, but I can sort of read it enough to look at it and go, that's bad or kind of good-ish. That's the level I'm at with assembly.
Or pretty much be the same across machines.
Yeah, okay. So yeah, question about, yeah, are these going to be the same? Yeah, these will be pretty much the same. I'm not sure about LLVM. It might have some target dependent stuff. I don't know. I never read that one. And the compiler people, other like low-level compiler people tell me to read this one and not code native, but I happen to know how to read code native already. So that's what I always use. They keep telling me I shouldn't. Yeah, anyway, that's all there is time for. I'm surprised by having not time for the last demo I was thinking of doing. Any more questions? And thanks for coming. It's been great teaching you all.
Let me just thank, I'll grab the microphone.
Oh, yeah, you can.
Thank you, Claire. So thanks for those who came in person and for people at home and at YouTube and the class. This was the first time we had Claire teach. She's an incredible contributor to the Julia language. You probably spoke about the work you're doing in compilers during the way. There's much more. Feel free. Are you happy for people to be in touch with you after the course via LinkedIn or other means?
I don't use LinkedIn.
Oh. Okay.
I have an account which is ancient, but don't go looking at that. Yeah, like come and look at my projects on GitHub if you want.
Oh, yeah, GitHub is a place to be.
GitHub, yeah.
It'd be very nice if we get a round of applause for Claire, and thanks a lot for running those 2 sessions. And yeah, as with any UQ course, feel free to give us feedback, good, bad, most importantly, constructive on all facets. And good luck with Project 3. Thanks.